So it's my great pleasure to introduce Jakob Foerster from the University of Oxford, who's actually come the least distance to give a talk tonight. We've had Mike from Leiden and Vanessa from, where's Vanessa gone, from Copenhagen. So you've just come down the road for an hour and 20 minutes.
And he's the latest.
So, I'm quite privileged to be here with So this was the preamble. But I think I also want to put this into context because in this talk, in this brief overview I'll give you, I'll not be working on large-scale games. I'll not be working on like large problems that you see in the news. What I try and get across is that even some quite simple looking things on the surface are really, really hard once we start asking questions. And in particular, if you think about the sort of big success stories that we've seen in the news, this has been about poker, diplomacy, as in fully competitive settings. Does that make sense? We've seen a lot of success where we can beat humans at a large number of games. But the question is, how do we deal with settings where we have different players pursuing different interests? Because obviously, we know that self-driving cars that will never exist actually aren't just in one homogeneous crowd pursuing one objective, right? So this would be, imagine that when it was completely dominating the world, then we could optimize one global system towards one goal, which is the maximization of profit for Alphabet. But we know this isn't the world we live in. We instead have a system of multiple different actors pursuing different goals. So this is called a general sum system. Does that make sense for everyone? It's when different players pursue different objectives. And what I want to get across to you in the next 15 minutes is why this is a hard problem from a machine learning point of view and how we can make progress on this. Okay? This is just one aspect of the sort of things that I'm interested in, which is generally speaking, settings where we have feedback effects, where multiple learning systems interact in the same environment. Let me give you a less obvious example. We think of machine translation as consisting of pairs of language, where we have an input, say English, and we're mapping into a desired output French. That looks like the most vanilla supervised learning problem, right? So where's the interaction with other agents here? Why is there still somewhere I have to consider the learning abilities of others? Well, because the users might want to take my machine translation system and actually build websites and translate them, which then feeds back on my training data. Does that make sense? So there's actually a lot of systems there where we do machine learning and we think this is just the standard single agent supervised learning problem, but in reality there's other agents, other actors that are interacting with my system, closing loop. And so my lab is interested in what does it mean fundamentally to do machine learning when other players in the world are also learning in the same environment. That is the fundamental question of mine. And who here knows of the prisoner's dilemma? Cool. Who wants to play the prisoner's dilemma with me? Anyone brave enough?
I'll take you on.
You'll take me on? Let's do it. So we do 1, 2, 3, and then on 4, it's a thumbs up, cooperation, thumbs down, defection. We both do with eyes closed. You have to stand up. Are you ready? Mm-hmm. 1, 2, 3, go! Okay, thank you very much. So what just happened here? Can anyone in the audience please talk me through what just happened? Was this a failure of decision making or not? Please, anyone. You all know the dilemma, what's going on here? I saw so many hands up. Please, what just happened? Yes.
Both parties squealed on each other, so you both got an extended prison sentence.
Yes, we all spent 2 years in prison, but at least we're in prison together. It's going to be delightful. So okay, but joking aside, wouldn't it be much nicer if we both had cooperated on each other? Right? They only spent 1 year in prison. Right? So now this seems like kind of annoying. Right? So let's now replace, we go forward. We're not playing the game ourselves. We're instead going to deploy machine learning systems that rob banks on our behalf, that get caught on our behalf, and get interrogated on our behalf, but we go to prison if they defect. Big caveat. What do you want your machine learning system to do if interrogated in that same situation? What do you want?
Cooperate?
You want it to cooperate?
No.
That's interesting. What do you want? So you have a robot, right? You and I both have built robots. We've trained them in simulation, and we're now testing them, right? And I'm sort of, what do you want your robot to do in that same situation, acting on your behalf? What do you want?
The higher sentence.
The higher.
Yeah.
So you want your robot to? Do you want it to cooperate or defect? What do you want?
I want it to cooperate and I defect.
You want. So no, you're being represented by your robot. So your robot is acting on your behalf. What do you want your robot to do?
Whatever gives us the least prison time.
Yes, correct. And what is that?
Defect.
Yes, thank you. Okay. So this is absolutely crucial. We actually want robots to defect in this single shot business dilemma. This is quite bizarre because there's a lot of people working in general sum games, in general sum learning, who are building methods that cooperate in this single shot business dilemma. It's quite weird, isn't it? Because I don't want that robot. Does that make sense? So that's important. In this talk, I'm not assuming that I'm God, I can change the reward functions of other players. I'm assuming I actually have to convince principals, such as you, to go out and use my methods. Because if I had a robot, if you came to me and trying to sell me a robot system, and I knew this thing cooperated in this single shot business dilemma, I just wouldn't use that robot.
But in the real world, you just trash the reputation, right? The real world is not single shot.
Aha, fantastic. This is not, by the way, we didn't agree on the script. This is all made happen, it's all called zero shot coordination happening here. Right? So this is precisely it, yes?
Have the rules of the world being transparent. Everyone knows it's going to collaborate. You mean into the game.
Yes. So this is now we get to like this is fantastic open source game theory. Yeah, but we do want to eat pizza or not. So this is, you can go there, right? In reality, Sarah's absolutely right. We do not play zero shot business dilemma or single shot. I mean, we do, but we try not to, right? And instead we play iterated games. So now, because you said it, so we play the iterated game. And somebody can please randomly be the environment and terminate that process after some time. Are you ready? The same rules apply. Eyes are closed. 1, 2, 3, 4. Okay?
Yeah.
1, 2, 3, 4. Okay. 1, 2, 3, 4. 1, 2, 3, 4.
Pizza.
Yeah. So I think we got it. Okay? So what just happened? You want to talk us through your reasoning process.
I was going to play tit for tat. I'm going to change my mind at the end.
Why?
Oh, you know, it's complex. It's concentrates. It's a long-studied game, right? There's many different strategies. It's iterated precision.
Correct. So in reality, we play these games where agents interact over and over and over again. That's what we designed. Society is structured around reputation, around repetition of games. And for the most part, that's how we get our social dilemma. But what actually happens when we deploy learning systems in these, I'm going to skip through a lot of slides because whatever, life is short. What actually happens if we deploy learning systems in these iterated business dilemma? Any guesses? So we're now doing reinforcement learning. Sounds fancy, just means we're going to maximize scores, right? Self-interested agents maximizing scores. And it's all the fancy stuff that you see in the news. AlphaStar, yay, OpenAI 5, super awesome, right? It's super fancy, it's like the best. Okay? So we take like the best thing that big tech has to offer, right? And we deploy 2 of these learning together. It's literally just self-play. This thing is so awesome. Yeah? Are you ready? What happens if we deploy self-play in the iterated business dilemma? Any guesses? What does it do? Yes.
It actually depends, I think you'll find, on the representation you're learning.
Here I did the simplest is I have a tabular game. I have an active critic algorithm that does exact gradients. I don't even need the critic, I have exact gradients. It's just standard, the most vanilla, the most simple, off the shelf reinforcement learning. What happens?
Mutual defection.
Yes. Mutual defection. And not just mutual defection, unconditional mutual defection. I took all the best. It was literally the best that you could offer. Right? This is what we do, softly. And that kind of makes sense. Because if you think about it, I initialized 2 agents. Well, both of them are like randomly initialized, set somewhat arbitrarily. And I now play a best response. But if you know I'm playing random, what is your best response?
Defect.
Correct. You better play mutual defection, right? And once you're defecting, I show the defect. Does that make sense? And that's shown here. So I've initialized 30 of these runs. This is really all plot by now. And I'm looking at the probability of cooperation on each of the possible 5 states. This is again the simplest setting you think about. I have 5 states, the initial state, and then the last action of me and you, 2 by 2, 5 states in total. And this shows you the different colors for the probability of cooperation on the x-axis for me and the y-axis for you. And basically what effect is about. Does that make sense? Yeah. So that is what we're at. And that was in 2017. And ever since we've been trying to make progress on this problem. And it turns out that there's a very simple algorithmic idea that we had back then that allowed us to actually address this. And this is a bit of formulas. So I'm wondering if I should use this diagram instead to explain it. But I'm not sure which one is it.
Use a diagram.
Yeah, this comes from a meme, right? But what we have is we have 2 players, right, that are both taking actions based on some policy. But now I have a learning process that updates that policy in the outer loop. Does that make sense? So we're playing that game over and over. We both have some policy in our minds, and then we update our policy after each episode. Does that make sense? And that was also what was done in naive learning. So here this was done using reinforcement learning. So based on my policy and your policy, I update my policy in the next step. That was naive learning, where I assume that you're just part of the environment. That's what everyone does, naive learning. Self-play, all these things, all that same stuff that's so awesome. It's in science papers and nature papers. Does that make sense? It's really good, but it just affects unconditionally. So I mean, sometimes I should put a caveat here. Sometimes it's really good to be unconditionally defecting. This is something that we sometimes forget. Defection sounds nasty. We want to have cooperation, but if you think about pricing and companies in a market, what does cooperation actually mean? What does it mean to play tit for tat? As price collusion, right? It's a funny thing because if we set prices above market, both of us, then we both make more profit. But if one of us lowers the price, they get a greater share of the revenue. Therefore, there's pressure to defect. So we have to be a little bit careful when we say, oh, cooperation is great, defection is bad. Not quite, right? But I divulge. So here we are. So what does this mean? We now have a mechanism which says, let me not just do reinforcement learning, I have this new magical learning rule. And what that magical learning rule says is I'm going to model other players as learning agents. And this is really implicitly what we do when we come to tit for tat. There's an underlying knowledge. Simon isn't just going to play that same strategy throughout. He's going to look at what I do and then update his policy based on that. He's going to learn and react, in the knowledge that I'm also a learning agent. And the question was, how could we bring that knowledge that other agents in the world that exist are learning from our interaction into a learning algorithm? And this is what our algorithm did, learning with a full learning awareness. And in particular, we're going to get a little bit technical. Apologies. But I mean, this is now where I'm a real machine learning person as opposed to game AI. I'm allowed formulas on my slides, right? This is cool, no? Oops. And I clearly don't know how technology works either. So what we're doing here is we're saying, okay, actually I have a value function. This is my expected return when playing Prisoner's Dilemma. And this depends on my policy. And it also depends on your policy minus I. But rather than differentiate with respect to my weights at the current policy parameters, I include the fact that you're going to be learning in the next time step. Does that make sense? Mm-hmm. I capture the dependency of your policy update on my actions. And suddenly, right, so if I'm just maximizing my current value, assuming that this is fixed, I'm going to lead to mutual defection. But if I account for the fact that other players in the environment are also learning themselves, it's pizza time.
But that was a lovely explanation.
Does that make sense? So suddenly I can differentiate through the learning step, and I can try and shape other agents in the environment into cooperation. And when we did all of this, and we now initialize 2 players, and we do the same thing again, we get to this lovely policy here.
Wow.
Can anyone tell me what this policy is? Beyond being colorful. Sorry?
Random?
Well, it has a bit of it's a bit scattered across different seeds, it's not perfectly reliable. But we have that same, so red was when both of us defected, we defect again. Blue was when both cooperate, we cooperate again. Green was I defected, you cooperate. Now I cooperate, you defect.
It looks a lot like tit for tat.
It looks at it for tat. Does that make sense? So just by accounting for the fact algorithmically that other agents are learning, I could suddenly get a policy out. I could discover tit for tat, which was this well-known policy that humans played in the business dilemma. Does that make sense? So this is something I just want to be very, very clear here. These are algorithmic advances. All of this was done on a single
Laptop.
on a laptop. So this you could nowadays run on your Apple Watch. This
On a
experiment.
Raspberry Pi.
Correct. You could run this anywhere. Does that make sense? And I did this at OpenAI, and Ilya Sutskever was running around like this. Nice one, Jakob. Have you tried a bigger RNN? Bigger recurrent neural network, bigger batch size? Because I showed him these defection numbers. I said, well, I'm sorry, I used the exact value function. That's like an infinite batch size. The precise dependence is the analytical function. It was an infinite batch size. Whoa! Does that make sense? So this is, I think, an example for what I did this work at OpenAI in my internship. I started this. One of the reasons I did it is because they came to me with a long list of sort of large-scale projects. I had just started as an intern. I said, "Oh, which project are you going to do?" I was like, "What project?" "Oh, we have this whole list." I was like, "Oh, haven't opened it, but thank you." And I just sat there and said, "I'm going to explore and I'm going to see what fundamental problems I'd like to address." Does that make sense? I'll give you now a 30-second sort of. This was 2017. It has lots of issues, and we fix all these issues. And if you want to. And if you want, it gets really powerful and it's really cool, but be warned and it's whatever. And we know how it works, but I won't tell you. Come talk to me afterwards. It's really nice. And then we did some other work, which is also really nice. So this is pushing it. Do you have 30 more seconds? How is the pizza doing?
Oh, I mean,
30 seconds.
the pizza's there, right?
Oh yeah, so this is, no one looks sort of, I can't see that, yeah. Everyone's still sitting down. So 30 more seconds, we pushed things farther, right? Because we said, okay, this was still about agents interacting in the same environment. What if I change the assumptions? They can't even interact. But what I can do is I can arbitrarily set a bit in your training data that's useless. So a cheap talk, and this is in the real world, you often have useless bits. So in the stock market, you have the order book, and if you're near the mid price, it matters. But there's loads of other values that don't matter. Does that make sense? There's often noise in the world that nobody cares about, but noise goes into the training. So what if I can actually perturb those useless numbers in someone's training set? And what we show in our paper, so Chief Talk, is that we can actually use this to then remote control agents. And I'll show you this a little bit. So this is, so we can fast forward. Oh, there we go. This is what I wanted. Fantastic. So here's basically this is the standard reinforcement learning task. This is what I mean by state of the art, right? It's really cool. This thing is trained to reach for the blue dot. So this is training. But at test time, we have these arbitrary noise bits, and we can now remote control this reacher to go to any other location that we want. Does that make sense? So this is like I say a cheap talk, and basically what we've done is we've now pushed component shaping to settings where I don't even interact in the same environment. But what I can do is I can control useless bits in the training data. And it turns out if I can have a meta-learning strategy that uses those useless bits in the training data to then remote control the agent at test time. So this is brand new work coming out of our nice little sideline lab at Oxford, and it works fantastically. And we know how it works. If you have any questions, ask us. So this is the summary. Well, thank you very much.